Doing today is going over the solving the logarithmic and exponential equations. Now 20 or 40 and 41, these here, there's two of them like this on the test, and the easiest way to see these, especially on the test in these form, variables in both exponents. There are ways to solve these without getting the bases to be the same. We haven't covered that in here, so especially if you see it on the test with variables in both exponents, get the bases to be the same. So for 40, we have 2 to the 2x plus 15. Well, 2 is as simplified as it gets. I can't rewrite 2 as a number to a power because 2 is prime. It's as simplified as it gets. So that kind of gives us a hint that I'm going to have to rewrite 8 as 2 to a power. And we could go and just start guessing, checking. 2, keep increasing the power by 1. 2 squared is 4. 2 cubed is 8. So that's what we need. And the nice thing, and I was at least nice on the test this way, one of them is going to be already to that base. Like this here. We have 2, can't reduce it. 8 is going to reduce to 2. One of them is going to be already in a nice form. Get the other one to match it. Does that make sense? Questions on how we started this? We feel good with this here? All right. Powers of powers. Multiply. 3 times x would be 3x. 3 times negative 7 is negative 21. Now, the reason we're doing this is because since the bases here are both 2, the only way that these two can be equal, 2 to the 2x plus 15 and 2 to the 3x minus 21, is if 2x plus 15 is equal to 3x minus 21. The only way that these two can be equal and have the same base is if their exponents are also equal, also have the same value. That's the only way this works. All right. So now we're just solving this equation. Does either x have a power greater than 1? Get x by itself. So we could subtract 2x. Telling us 15 is equal to x minus 21. Add 21 to both sides. Telling us x is equal to 36. That's it. I'll repeat this. I've repeated and said it before. None of the problems on this test are going to be no solution. There's going to be an answer. No solution is not an answer on these here. There are some cases I will bring that in and put that in, but especially for Algebra 2, I don't like using no solutions on these tests, mainly because y'all's first thought is not, oh, that is the correct answer. It's more, I did something wrong. No, I don't like having that on the test. So all the problems on the test will have a solution. All the solving will have a solution. All right. Let's look at 41. 512 to the 5x minus 1 is equal to 1/8 to the negative 4 minus x. Well, on this right-hand side, it'd be nice to have that 8 out of the denominator. Instead of having 1/8, we can move the 8 from the bottom of the fraction to the top, but that means that exponent, even though it doesn't have 1 written, it's 1, it has to go from positive to negative. Now, it'd be nice if we could rewrite 512 as 8 to a power. So we can see here 8 squared is 64, 8 to the third is, lo and behold, 512. So we can replace 512 with 8 to the third power. Now, 8 is indeed 2 to the third. We've seen that already, yes? I could take it all the way down to 2, but at this point here, are the bases the same? Yeah, it doesn't need to be in the lowest terms. They just need to be the same. So even though it could go lower, they're both 8. I don't have to take it lower than that. You'll still get the same answer. But we can stop here. Powers of powers multiply. Multiply by -1, giving us excuse me. Since the bases are the same, we'll set the exponents equal to each other as well. Solve for x. So we'd subtract x from both sides, giving us 14x minus 3 equals 4. Add 3 to both sides, 14x equals 7. Divide both sides by 14, telling us x is 1/2. Since x is our variable and it's inside or in the exponents and those powers, it could be positive, it could be negative, it can be 0. We can have any value of x that we want. Questions on the first two? We feel good with these here? We can look at 42, but 42 is the exact same thing. The bases are the same. Doesn't matter that they're both e being irrational, they are the same value. So it still means that the exponents have to be equal. That's really all it's saying. E to the 4x plus 7 equals e to the 6x minus 35. Bases are the same, so the exponents have to be the same as well. At this point here, we can just solve for x. We can subtract 4x from both sides. 4x minus 4x is 0. Telling us 7 is equal to 2x minus 35. We can add 35 to both sides. Telling us that 2x is equal to 42. Divide both sides by 42, telling us x is 21. That's it. Feel good with these here? Let's look at 43. There's no way to get the bases to be the same. Because if they were, we would need 2 e's just like the last one. So since the bases aren't the same, we need one term on either side. We need the base with the variable and the exponent on one side, everything else on the other. So the first thing we can do to get this e to the x by itself is to add 7, because the -7 plus 7 would be 0, leaving us with 2e to the x equals 12. E is not by itself, so we would divide both sides by 2, telling us e to the x is equal to 6. Okay. And that's the first main step in solving with unlike bases, to get that one term on either side. Second step is to get the variable out of the power or log. If it's in a power, we're going to use logs, depending on the base. Since the base is e, we use natural logs. If the base is a number, we're going to use logs. And the reason we use logs is our power property. The power property of log says that we can take that exponent and put it in the front, giving us x times the natural log of e equals the natural log of 6. What is the natural log of e? 1. So that is 1. 1 times x is just x. Is x by itself? Yeah. And that's as far as I'm going to have you take it. I'm not going to have you evaluate or find the approximate value of the natural log of 6. Because x equals the natural log of 6. You solved it for x. You solved the equation. That next part is less solving and more just evaluating for the log. We have a whole other section for that. Leave it for there. Questions on this here? Do we want to see another one like it? Or do we feel good with those? We can do 644 if we want. Yeah, okay. 6e to the 2x plus 1 plus 9 equals 15. We need to get that base with the variable and the exponent by itself, so e in this case. So the first thing we're going to do is subtract 9. Telling us that 6e to the 2x plus 1 is equal to 6. Still not by itself, so we're going to have to divide both sides by 6. Telling us that e to the 2x plus 1 is equal to 1. What logarithm would we apply to both sides? Natural log, ln. And the reason we do that is to get that exponent to the front. And we do this because the natural log of e is 1. So I do that mark through kind of the arrow just to signify that that's values 1. We're replacing it with 1. Now something that's interesting is the natural log of 1 is 0. Doesn't matter what it is. Log of 1 is 0. So if we notice that the natural log of 1 is 0, we can replace it with 0. Solve for x. Minus x is negative 1/2. Now, if you'd gotten that x is equal to the natural log of 1 minus 1 all over 2, I will take that. That is the same answer. We wouldn't normally leave it in that form, but I will take it. Because essentially that's what we did. We just didn't evaluate the natural log of 1. But I'll take either one. Questions on 44? Let's look at 45. 7 to the x is equal to 3. Yes? Do we have the base with the variable and the exponent by itself? Yeah, it's not one term on that side, one term on the other. So we can use our logs to get the variable out of the exponent. Now, since the base is not e, we're going to use log. And I'm going to use the specific log for this one. Its base is going to be 7. The reason we use logs was to get the variable out of the exponent, telling us that we have x times log base 7 of 7 equals log base 7 of 3. Now, the main reason I used log base 7 for this here is because log base b of b is 1. So log base 7 of 7 is 1. telling us 1 times x is equal to log base 7 of 3. Is x by itself? Yeah. And that's as far as we have to take it. All right, we can go on and look at 46. Well, with 46, 1 term on either side, yes? So we can go on and apply log base 11 to, to both sides. Exponent's going to move to the front. So 6x plus 2 times log base 11 of 11 is equal to log base 11 of 38. The whole reason we use log base 11 of 11 is because it reduces to 1. Cancels out. Telling us that 6x plus 2 is equal to log base, don't know why I wanted to write 2 there, 11 of 38. Is x by itself. Now we just have to solve. Minus 2 from both sides, telling us that 6x is equal to log base 11 of 38 minus 2. Still not by itself, so we would divide both sides by 6, telling us log x is equal to log base 11 of 38 minus 2 divided by 6. And that's it. I'm not asking you to take it any further than that. Questions on this here? We're ready for 47. Kind of like the first first 3 that we did. Here we have the natural log of 3x plus 2 equals the natural log of 4x minus 5. When we have the same log equal to each other, the only way that these two logs can equal each other is if what's inside each log is also equal. The only way that we can have two natural logs equal to each other is if what's inside is equal as well. X isn't to a power, so we just need to solve for x. Minus 3x from both sides telling us 2 is equal to x minus 5. Add 5 telling us x is equal to 7. Here we don't have to worry about it, but again, the value of what's inside the logarithm, 3x minus 2, 4x minus 5, cannot be 0 or negative. If we have a value of x that makes that 0 or negative, it doesn't work. We cannot have a value for that. Questions on this here? Let's see here, we'll look at one more of those. Let's look at this one here. Ooh, I need to fix that. That is blurry. Now, log base 2 equals log base 2. They are the same log. So what's inside, our x squared minus x minus 6 is going to equal negative x, because the only way two logs can equal each other and be equal is if what's inside is the same. Here we do have an x squared term, so we need to get this equation equal to. 0. So we can do that by adding x to both sides. Those two will cancel. Incidentally, these will cancel, telling us x squared minus 6 is equal to 0. At this point here, we can try to factor. It's not going to factor. I can tell you that right now. But since there is no middle term, there's no x term, square root method, get x squared by itself, take square to both sides. And this only works if we don't have an x term. So what we can do is just add 6. Because what we're saying is something times itself is equal to 6. If we don't have a middle term, x squared by itself. Everything on the other side, and then we can just square root both sides. Because the square root of x squared is x. Anytime we take the square root of both sides, we have to add the plus or minus. Because the square root of 6 squared is indeed 6. Negative square root of 6 squared is also 6. So we do have both. X is by itself, so we've solved for that there, yes? I will say there are a few problems on the test where we do get 2 values for our logarithms. If that does show up, check them. Because what's inside the log cannot be negative or 0. Well, let's start with the negative square root of 6 first. And we'll plug it back in. Square root of 6 squared minus negative square root of 6. Because all the ones we had in class and on the homework, the negative case was the one we normally threw out. So if we look at this here, negative square root of 6 squared, we already saw that 6. Negative square root of 6 is going to be positive square root of 6. Minus 6 is equal to log base 2 of negative square root of 6, which is positive square root of 6. 6 minus 6 is 0, telling us log base 2 of the square root of 6 equals log base 2 of the square root of 6. Even though square root of 6 is irrational, doesn't matter. They are not 0 or negative, so that is a true statement. So our negative square root of 6 works. Let's look at the positive square root of 6. Log base 2 of the square root of 6 squared minus our square root of 6 minus 6 is equal to log base 2 of negative square root of 6. When we simplify the right side, simplify those parentheses, we end up with log base 2 of negative square root of 6. That cannot work because what's inside here is negative. So the positive case doesn't work, telling me that x has to be negative square root of 6. So it is some cases where the negative case does work. The negative case is the solution. Because even on the other side, these two end up canceling, telling us that we have negative square root of 6. Yes, we do have the same thing on either side, but log base 2 of negative square root of 6 doesn't exist. So we have an invalid 2 non-existent numbers on either side. It doesn't matter that they're the same, they just don't exist, so this doesn't work. Does that make sense? Yeah. So it is good, especially if you get 2 solutions to check them. Check them. Questions on 50? Okay.
Will we have any of the tests that we use the quadratic formula for?
No, there's one on the review, but none on the test. None on the test. You can solve all of them by factoring or the square root method. Square root method will work too. Because you can use the quadratic formula to solve them, but don't need to. Factoring, graphing, and square root method will do everything you need. All right. 51, why don't we look at it first? Log base 7 of 4x plus 9 equals 2. We do have one term on either side, log on one side, number on the other. Yes? So that means we can put both sides to its base to get the variable out of the log. Because 7 to the log base 7 will simplify out, leaving us with 4x plus 9. Putting it to the log base 7 to the base of 7 is going to simplify that log out, leave us what's inside the log. Now the question is 7 squared a nice number? Yeah, it's 49. If that other side does simplify nicely, simplify. If it doesn't, leave it alone. We don't have any squared terms, so we just need to solve for x. Minus 9 from both sides, telling us 4x is equal to 40. Divide both sides by 4, telling us x is equal to 10. Done. We good with 51. 52. Natural log of 6x minus 2 equals 7. Natural log's by itself. Numbers on the other side. So we can put both sides to the base of the natural log, which is e. Because our e and ln will cancel, leaving us with 6x minus 2. Now the question is, e to the 7th, is that a nice number? No. E is irrational, so putting it to the 7th power is not going to give us a nice number. So we can leave it as e to the 7th. Now we just need to get x by itself, so we can add 2 to both sides. 6x equals e to the 7th plus 2. And then lastly, we're going to divide both sides by 6, telling us x is equal to e to the, don't know why I just drew a 6. E to the 7th plus 2 over 6. Questions on this here? Questions on 53 or 54? I think we feel good with 53. 54 is a little bit different because the natural log is not by itself. We don't have one term on either side, so we have to get one term on either side. And to do that, we're going to add 4, telling us that the natural log of 6x is equal to 19. Now that we do have one term on either side, we can put both sides to the base of e to get e to the ln to simplify out or simplify down to 6x is equal to e to the 19. Solve for x, we would divide by 6, telling us x is equal to e to the 19th over 6. And that's it. Yes. Questions on this here? We feel good with 54. Okay. We're going to skip 55. 55 is the one on the review sheet you have to use the quadratic equation to get the answer. It doesn't work out nicely. There is one like this on the test. Two. One's on the test, one's bonus. But again, we need one term on either side of the equal sign. However, we have two logs. But since we have two logarithms being added together, we can rewrite it as a single log with what's inside being multiplied. It's our product rule. So log base 2 of x plus log base 2 of x minus 2 is the same as log base 2 of x times x minus 2. Because what's inside each log is being multiplied together. Even though it's not written, it's understood that there are parentheses around that x there. Now it's the same thing as what we were just doing. And this here, we're going to put both sides to the base of 2. So that our 2 to the log base 2 will simplify down, leaving us with x times x minus 2 is equal to 2 to the third, which is 8. Now on the left-hand side, we can distribute that x. X times x is x squared. X times negative 2 is negative 2x is equal to 8. Now we do have an x squared term. We do have a middle term, so we are going to have to get this equal to 0. Now this will factor. The other thing we can do is graph it. So we can say x squared minus 2x minus 8 and hit graph. And we're looking for where the equation is 0. We're looking for where it crosses the x-axis. So we can see the 2 points there, or we can go second graph and look for when y is 0. When x is negative 2, the y value is 0. When x is 4, the y value is 0. Telling us that the values of x are negative 2 or 4.
Does that work when you have to like use a quadratic formula?
It will if the numbers are nice. If they're not nice, it does work, but we have to do other steps beyond what we just did to find them. Because the table works well with nice numbers. We can try to find the not nice ones, but you'd almost have to know what radicals or what scale to put it on to find them. So it's almost you have to know it to find it. It works, but it's very tedious.
So it's just easier just to plug it into the
Quadratic formula at that point, yes. Two solutions, it'll be good to check. We can start with negative 2. Well, we can almost throw this out immediately. In both spots, log base 2 of negative 2, we cannot have a negative inside that log. If we do, we know that doesn't work because we can't take log base 2 of negative 2. We also can't take log base 2 of negative 4. So that tells me negative 2 does not work. It's not a solution. Log base 2 of 4 is fine. 4 minus 2 is 2. Okay. We're good there. Because log base 2 of 4 is fine. We don't have a negative or 0 there. Then we have log base 2 of 2. That's fine as well. Both of those work. So log base, or x equals 4 is our one solution that works. Because negative 2 gave us a value of x that does not work. It gave us 0 or negative inside that log. Questions on 56? 57 through 59 were inequalities. Solving inequalities is going to be essentially the exact same thing as solving equations, except we have inequality signs instead of equals. The restrictions are the one thing that normally gets us a little tripped up, but none of the problems on the test, the restrictions come into play. We don't even have to worry about them. But the steps still hold true that we've been using. So for 57, one term on either side. We do indeed have one term on either side. So we'll put here, since we start as a log, we're going to put both sides to the base of the log. So e to the ln is going to cancel, leaving us with x minus 1 is greater than or equal to e to the 9th. E is not a nice number, so putting it to the 9th power is not going to just make it a nice number. We can add 1 to both sides, telling us x is greater than or equal to e to the 9th. Normally, this would be one of the problems that we might have a restriction on. And if we were looking at the restriction, it'd be that what's inside, x minus 1, would have to be greater than 0. Or telling us that the values of x have to be bigger than 1. Well, e to the 9th plus 1 is indeed bigger than 1, so we don't even have to worry about those. So that's the answer. Questions on 57 before we look at 58. 58. We put both sides to the base of 7 so that our 7 to the log base 7 will simplify, leaving us with x plus 2 is less than 7 to the 4th is a nice number, 2401. Now we need to solve for the value of x by subtracting 2, telling us x is less than 2,399. Now the restriction for this one here, again, that x plus 2 has to be greater than 0. Or essentially that x has to be greater than negative 2. Now negative 2 is indeed less than 2,399. So here we'd have to add back in the fact that negative 2 is less than x is less than 2,399. The values of x have to be between those spots for it to work. We're not going to have, if we had one like this, instead of having that sign be less than, it's going to be greater than, making the restriction not worry about it, because negative 2 would not be greater than our 2,390. So the restriction doesn't have to work, or it doesn't come into play, because they aren't a part of the solution. Does that make sense on this here? Questions on 59 or 60? Either one of those that y'all want to look at. We good with these here? Just get the log by itself and put it to the base. Same with this here. The only time we have to, it changes if we multiply or divide by a negative. You got to flip that sign. If we look at 62, since we started out with a variable in the exponent, we got to use our logs to get the variable out. So for this here, we're going to apply log base 3 to both sides. Variable comes out of the exponent, times 4x minus 5 times log base 3 of 3 is greater than log base 3 of 108. Again, just like before, log base 3 of 3 is 1. And 1 times our 4x minus 5 is just 4x minus 5. Now we just need to solve for the value of x. So at this point here, we can add 5 to both sides, telling us 4x is greater than log base 3 of 108 plus 5. And lastly, we would divide both sides by 4, telling us x is greater than log base 3 of 108 plus 5 divided by 4. And that's it. Now, since x started out as an exponent, it doesn't matter what the values are. We can add any value in there. So we don't even have to worry about restrictions for those. Questions on 62? Questions on 63 or 64? Either one of those that y'all want to see worked. So we're good with those there. So underneath these, because I think those are the last two problems, yes? Change of base. Change of base. Log base 15/7 of 97 101s. Change of base is, I'm going to ask these problems on the test. I forgot to put them on there, but they're not that big a deal. What the change of base formula is it says that we can take log base b of m and rewrite it as log of m over log of b. This is common logs. We're rewriting the base as base 10. We can also do this with natural logs. Okay. Looking at this here, log base 15/7 of 97 over 100. And looking at that there, so we're going to do common logs first. What is m in our example here? See what's inside, yes? So 97 over 100 and 1. So we'd have it on top. Over log of b, log of the base. So b is 15/7. So rewriting this in terms of common logs would be log of 97 over 100 over log of 15 over 7. Questions on the first half of it? We're ready to write it in natural logs. Essentially, it's the exact same thing, but instead of log, we write it as natural log because we're changing the base to whatever we want. Changing the base of that log. For the first two, we changed it from base 15/7 to base 10. Base 10 over base 10. Log of base 10 over log of base 10. The second one, we just changed that base from 15/7 to base e. They give us the same value. This here is nice when we don't have a graphing calculator to calculate this. We can actually change it into something that would work on most any calculator. Any calculator can take log of 97 over 100 divided by log of 15/7. That's it. Questions on this here? Because, I mean, I did this one here just to iterate the fact that it doesn't matter what the number is, we can do it. It's going to follow this process the exact same time. Questions on this here? There are 6 problems like this on the second part. 14 solving.
So they're just going to ask us to, like, do one of those or both of them?
Both of them, yeah. So it's going to give you, so every single problem, I can't remember, is going to start off like this here and ask you to rewrite in both. That's it. Don't have to simplify the value. That's all I'm looking for. Questions on this here? And that is, I mean,